The research paper presents an enhanced weak superconductivity in trigonal gamma PtBi2, a unique material with topological properties. Electrical resistivity experiments reveal superconductivity at Tc equals 1.1 K, accompanied by an enhanced critical magnetic field Hc2, 0, of 1.5 Tesla and a low critical current density Jc, 0, of 48 per square centimeter. The superconducting transition becomes broader and asymmetric under a magnetic field, indicating an inhomogeneous superconducting state. The material's properties are influenced by its topological nature, characterized by Dirac-like cones and a large magnetoresistance. The authors emphasize the material's potential for further study in topological matter physics, particularly in the context of superconductivity and its relation to topological phases. The onset of superconductivity in beta PtBi2 and gamma PtBi2 is characterized by an abrupt increase in carrier concentration and a sudden drop in mobilities. In gamma PtBi2, a sign change in the Hall coefficient occurs exactly at the pressure onset of superconductivity. Local enhancement of superconductivity is observed in point contact spectroscopy experiments, with a critical temperature of 3.5 K and an upper critical field of 3T. Scanning tunneling microscopy experiments detect superconducting gaps as large as 20 MeV, robust against magnetic fields and temperatures up to 5 Ka. RPES experiments combined with ab initio calculations identify topological surface Fermi arcs that become superconducting at T tilde 10 K. The authors report their findings based on electrical transport results on a high-quality single crystal of gamma PtBi2, detecting a superconducting state with a doubling of the critical temperature, Tc equals 1.1 K, and almost an order of magnitude enhancement of the critical field, μ0 Hc2 greater than 1.5 T, with weak anisotropy. The magnetic susceptibility, chi T, exhibits a pronounced temperature dependence for magnetic fields applied along the axis, chi-c, and perpendicular to it, chi-ab, as shown in Figure 2. Measurements were conducted using a LR700 AC resistance bridge or in DC mode with a high-gain EM810 preamplifier and a Keithley 220 current source. The temperature dependence of the zero-field electrical resistivity, depicted in Figure 3, reveals a metallic behavior with an extrapolated residual resistivity, ρ0, of approximately 0.13 microohms cm and a residual resistivity ratio, RRR, of around 320, comparable to the best samples in the literature. A prominent magnetoresistance, Mr. 2K, 9T, equals 41, is observed at low temperature, which is linear in field above micro 0H equals 10T. The magnetoresistance is temperature independent below 4 K and is drastically suppressed above 25 K. No Shabnov-de-Haas oscillations are observed for the H-barred BL 001 field direction, but they emerge as the field is tilted away from this direction, in agreement with previous reports. Differential scanning calorimetry (DSC) is used to investigate the phase stability of the gamma PtBi2 single crystal. Figure 4 displays the temperature variations of the heat flows during two successive heating sweeps, revealing phase transitions assigned according to the PtBi binary phase diagram. The first run shows a wide exothermic peak above T approximately equals 200 degrees Celsius, signaling a progressive transition from the metastable gamma phase to the stable orthorhombic alpha phase. The equilibrium transition from the alpha phase to the beta phase occurs at T equals 270 degrees Celsius, with a broad exothermic peak extending above this AB transformation, indicating incomplete retransformation of the metastable gamma phase into the stable phase. A large endothermic peak is observed around T equals 420 degrees Celsius, corresponding to the equilibrium BG transition. The second run shows only the BG transition, indicating the metastability of the gamma phase at room temperature. The research on the superconductivity in the gamma PtBi2 compound discusses the experimental results, focusing on the equilibrium transitions observed in dilatometry measurements. These indicate a slow cooling process allowing for the successive BA retransformation. Resistivity measurements at very low temperatures reveal a superconducting transition with a critical temperature Tc equals 1.1 K, defined by the 50% criterion. The transition is narrow, with a 10%-90% criterion width delta Tc equals 0.1 K for applied currents I is less than or equal to 0.1 mA. As the applied current increases, the transition broadens and shifts to lower temperatures. The magnetic field suppression of superconductivity is also observed, showing a well-defined superconducting transition even for strong magnetic fields. This is confirmed by ρh data measured at T approximately equals 0.2 K with I equals 0.1 mA, depicted in Fig. 5. The HT phase diagram, presented in Fig. 6, shows the critical fields micro 0 Hab C2 approximately equals 1.25 T and micro 0 HCC2 approximately equals 1.85 T, indicating an anisotropy coefficient gamma approximately equals 0.7. The corresponding coherence lengths are Xi ab approximately equals 13 nanometers and Xi C approximately equals 19 nanometers. In the superconducting state of gamma PtBi2, critical magnetic field dependencies exhibit unique characteristics. The critical field ratio H, T, is expressed as a function of reduced temperature T, with the exponent alpha serving as a fitting parameter to describe the curvature of the data. Notably, the data reveals a large positive curvature, particularly in the low-field region, indicating an upward curvature close to the critical temperature Tc. An uncommon feature of the critical fields is observed, where HabC2, T, less than HCC2, T, attributed to the anisotropy in the coherence length values. This contrasts with other layered compounds, where complex HC2, T, behaviors are typically explained by varying coupling among superconducting layers or multiband effects. The study suggests that inhomogeneities in the sample may influence the superconducting state, despite the high-quality sample. The asymmetrical transition width in ρ, T, at fixed H provides evidence for the presence of such inhomogeneities. This finding has implications for understanding the role of inhomogeneities in shaping the superconducting properties of gamma PtBi2. Trigonal PtBi2, a topological material candidate, exhibits enhanced superconducting properties in high-quality single crystals synthesized with a residual resistivity ratio of 130, significantly higher than previously reported values. This improved crystal quality leads to a higher superconducting transition temperature of 1.1 K and a critical field at least 5 times larger than previously observed. Notably, the study reveals a small critical current, suggesting an inhomogeneous superconducting state within the bulk of the crystal. The physical properties of PtBi2 are characterized by thermal expansion, electrical resistivity, and magnetic susceptibility measurements. These results hint at the material's potential to exhibit topological behavior, possibly featuring surface or 2D superconductivity. The authors emphasize the need for further macroscopic and spectroscopic studies to fully elucidate the properties of PtBi2. The high-quality crystals enable the investigation of PtBi2's superconducting properties, including the temperature dependence of the upper critical field, which is described by the Wertheimer-Helfand-Hohenberg model. The study's findings provide valuable insights into the material's potential for hosting topological superconductivity, warranting further exploration. Overall, this research highlights the promising superconducting properties of PtBi2 and underscores the need for continued investigation to fully understand its behavior and potential applications. The research paper presents a thorough examination of the current state of quantum error correction, focusing on the development of robust and efficient methods for mitigating errors in quantum computations. Quantum error correction codes, such as the surface code and the Shor code, are essential for large-scale quantum computing. However, these codes often require significant resources, including multiple qubits and complex quantum gates. To address this limitation, the authors propose a novel approach based on the concept of non-abelian anyons, which can be used to encode and correct quantum information more efficiently. The authors begin by reviewing the fundamental principles of quantum error correction, including the quantum error correction threshold and the concept of fault-tolerant quantum computing. They then delve into the specifics of non-abelian anyon-based codes, which leverage the exotic properties of these quasi-particles to encode quantum information in a more robust and compact manner. The paper presents a detailed analysis of the performance of these codes, demonstrating their ability to correct errors with high fidelity while reducing the resource requirements compared to traditional quantum error correction codes. The authors also discuss the experimental feasibility of implementing these codes, highlighting the potential for near-term demonstrations using existing quantum computing architectures. A key contribution of this work is the development of a novel algorithm for encoding and decoding non-abelian anion-based codes, which is shown to be efficient and scalable. The authors also provide a thorough discussion of the limitations and challenges associated with these codes, including the need for further research into the stability and control of non-abelian anions. Overall, this paper presents a significant advancement in the field of quantum error correction, offering a promising new approach for building robust and efficient quantum computers.